Okay, so if we take this Hamiltonian operator and we apply it to our arbitrary wave function, and then um, we basically take the inner product of that with the wave function. So we multiply that by the complex conjugate of the wave function, and we integrate over all space. And again, this depends on the geometry. For a 1D potential well, you go from 0 to L. Then what we'll get back is the expectation value of the energy, or the average value of the energy. Okay, so that's what I've shown here. The expectation value of the energy is equal to the Hamiltonian operator in the Dirac notation. It's equal to the Hamiltonian operator operating on the wave function, and then the inner product with itself, with the wave function. Okay, and and again, if we write it out in the notation that we've been using, psi star is just a linear superposition of the basis states. Here I'm using an index m. I want to keep, for the moment, I want to keep my indices for psi star and psi different, okay, just to be completely general. All right, and so psi star is again a linear superposition. So we have the linear superposition of the basis states, and then we take the complex conjugate of that. That's psi star. We have the Hamiltonian operator, and then we have the linear superposition again of the states, of the basis states psi sub n. And again, now I'm using a different index n. Okay, I'm just doing this to be completely general. You'll see in a second how this works out. So if we then bring both of these sums outside the integral, we bring both of the amplitude coefficients, the Cm star and the Cn, out of the integral because they don't depend on x. And we bring the energy out. Where does the energy come from? Well, we have the Hamiltonian operator operating on a wave function, okay? And what that gives us, well, it's operating on a linear superposition of the basis states, and on each basis state, when you have the Hamiltonian operator acting on a basis state, then what you get is the energy associated with that basis state back out times the Hamiltonian. So I guess what I'm saying is that H times psi is equal to E psi. Okay, and I've written that, I think, in a few lectures ago. All right, so that we can bring the energy out. Okay, and then we still have the integral. Now, when we do this integral, remember these basis states, the psi mn's, the psi m and the psi n's, these are orthogonal to each other. So an orthogonal set, a complete set, which means that if you this is the inner product of two basis states, and so this is 0 unless n equals m, and that basically can be represented by this Kronecker delta function. Okay, so this integral and the product of these two states is 0 unless n equals m, in which case it's 1. Okay, and so in the end, what we get is this expression, which, when you apply the Kronecker delta function, then m has to equal to n, and so you get the sum over n. The sum over m goes away. Okay, and because again, you only get a term. You only get one term out of that sum, and that's when m equals n. And so that's where this Cn star comes from, the Cn and the En, and then Cn star times Cn is just the magnitude squared. And so what we have indeed shown with this, as I said that we would, is that these coefficients squared here are equal to the probability that a measurement of the energy yields a particular value En. So that if you basically if you do a sum over n of the probability of finding the wave function in a particular state, you multiply that by the energy associated with that state, you get the average energy.